In our last lecture we talked about continuous functions and finding critical points for them. Excuse me. What we want to talk about today is two theorems that go along with the fact that we can find critical points. And to begin with, I want us to focus in on what does it mean for a function to be continuous. If we go back and we think about continuous functions graphically, what does that mean? That means that we've got a function that once we start drawing it, it never stops. We can always draw it with our pencil on the paper. We never pick up our pencil off the paper again. So this is what it means to be continuous. Now these are the functions that we're going to be dealing with mostly throughout calculus here, or at least we will limit our functions to a region that the function is continuous on. So let's start off and look at a theorem called Rolle's theorem. It's named after the gentleman that first published it. We've got a function that is continuous on a closed interval and differentiable on the open interval, and the function values are the same at each end. Let's kind of draw a picture of what that looks like, okay? So let's say that here's our point A and here's our point B, and we know that the function value is the same at each one. And we don't know what it is, but we know that if it's at this point on A, it's at the same place on B. Now, we know the function is continuous and differentiable. Well, on the last slide we talked about what it meant to be continuous. What does it mean to be differentiable? Differentiable means that there are no sharp turns. Okay? So as we look at this function, we know that we can draw it without picking up our pencil, and we can't have any sharp turns. So it could, for example, do something like this. Doesn't have to do that. It could be the simple choice of just a straight line across. Or it could be just one big arch up in the air, or one big arch down. Or it could do something like this, where it goes up and down and up and down and up and down. But you get the idea. It has to do something like that. So those are the type functions that we're talking about when we talk about Rolle's theorem. And what conclusion can we draw? Rolle's theorem says in there exists at least one C such that f prime equals 0. Well, now let's think about what f prime being 0 means graphically. Graphically, that means slope is 0, equation of a tangent line. So that means if we draw, there has to be at least one place on each of these functions, and you notice that on the green one there's only one, but on the red function there's two, and on the blue there's many places, here and here and here and here and here. So there's 5, and this black straight line, every point the derivative equals 0. And that's really all that Rolle's theorem tells us, is that if we've got the endpoints being the same height, then the function has to have at least one point in there where there is a critical point and where the derivative equals 0. Well, now let's think about what it means to be a critical point. A critical point means that it is a candidate for a maximum or a minimum. And as we'll learn later on, we're going to call this point here a local maximum, irregardless of what happens out here. So each of these points right here and right here on the blue line would be considered local max, and each of these points on the blue would be considered local mins, or local minima, because that's the lowest point in the area right around the point. But that's what we've learned simply because of Rolle's theorem. We know that there has to be at least one, and by using critical points we can find out what that one is. Now, this doesn't tell us what those points are, doesn't really tell us how to, but it tells us that they have to exist. And that's important to know sometimes, that there has to be one, then we can go on and use methods to find out what they are. Something very similar to Rolle's theorem is called the mean value theorem. and you will hear this one quite often as we move on through the course. You'll hear it referred to as the MVT, the mean value theorem. And let's read the mean value theorem. F is continuous on the closed interval, differentiable on the open interval. Here's a typo. F of A is not equal to F of B. Okay, so there's the difference between Rolle's and mean value. Rolle's, they're equal. Mean value, they are not. So let's get a picture of what that looks like. Here's our coordinate system, and we've got our point A and we've got our point B, and now we know that A and B are at different heights. Okay, the function value at A is different than the function value at B. Now it's continuous and differentiable, so we can surmise from that the function has to do something like this, or it could be a straight line between them, or just one kind of arc, but no matter what, it's got to get from one point to the other. Now what does the mean value theorem say? Well, let's look first of all at the right hand side here. F of B minus F of A over B minus A. I think if you'll look back at either week 3 or week 4 of the FRQs, you've had to use something like this. We had a problem where you were given a curve and the points P and Q on that curve, and you were asked to find the slope of the secant line, if I'm not mistaken, or the slope of the line between those two. This is the slope of the secant line, and this is not using any calculus on this right side. We're just finding the slope between these 2 points right here, A and B. And you've been doing that since Algebra 1. It's the function value, it's y2 minus y1, which is your F of B minus F of A, over x2 minus x1. So this right side is not calculus here really, it's pre-calculus, it's Algebra 1, it's things we've done there. What does mean value theorem say? That if we've got a secant line here, if we've got this going on, then there has to be at least one point in here such that if we draw that line, it's going to be parallel to this one. It's going to have the same slope as this line here. And if you'll look at this curve that we've drawn, it's actually got 2 of them in here. It's got this line up here and this line down here would have the same slope as this one here. So that's all that the mean value theorem says. If we've got a slope here, like we do, if we can find that out, then there has to be some point in here such that it's equal. Now we don't know what that is, but we do know that there has to be at least one. And if you'll go back and look at that FRQ I mentioned earlier, you actually did this process in that FRQ. You had to find this slope and then find the point such that this line was parallel to this line. That's exactly what we did. You used the mean value theorem to do that, even though you didn't know that it existed at that particular time. So you're going to use the mean value theorem and Rolle's theorem quite often and don't even realize you use them. I don't want you to get bogged down in the words right now. We're going to refer to them quite a bit over the course of the year, and you'll be able to refer back to it at a later time. But just I want you to get familiar with the terminology with it, mean value theorem especially, and knowing what it means to have it, knowing what all of these words up here are saying and having some idea of what it looks like. Well, what do these look like in usage in actual problems? Find the x-intercepts of the following function and show that the derivative has to equal 0. Notice it didn't say find the point where the derivative is 0. It said show that it has to be. So this is an indication that we're going to have to justify our answer. So first of all, it says find the x-intercepts. That means we set this equal to 0. We factor this side over here, x minus 4, x minus 2. So we get x-intercepts of 2 and 4. Okay? So let's go over here and draw out what that's going to look like. We know at 2 and at 4 we have x-intercepts. Alright? So now let's think about this. We've got a function now. We know we've got a continuous function because we don't have any fractions or square roots or ln's to worry about. So we've got a continuous function. We've got a differentiable function because we don't have any absolute values in there. So, and we just found out that f of 2 is the same as f of 4. So we've got all the criteria for Rolle's theorem here. So what does that mean? We can say now, since f is continuous from 2 to 4 and f is differentiable 2 to 4. Notice how I wrote those differently. 2 to 4 for continuity is a closed interval. 2 to 4 for differentiability is an open interval. Therefore, by Rolle's, there exists a C between 2 and 4 such that f prime at C equals 0. And that's all this problem asks us to do. Now, could you find that point? Sure you could. You could take the derivative, set it equal to 0, you'd find out that x equals 3, and suddenly you would know that it has to have a point in there, and you'd know what that point is. Furthermore, because you've had classes before this, you know that this is a quadratic because it's x squared, you know it's a positive, so then you would actually be able to sketch this function out. But you can see that if it was something we didn't know anything about the shape of the graph, suddenly we've got a lot of information about it just from this little bit of work right here. Well, let's go ahead to another problem. Find all values of C on the interval -3 to 3 such that f prime of C equals 0. Well, do there have to be any values? Well, let's quickly just decide that. What is f of -3? If we put that in there, we get 81 minus 27, which I think if we subtract that is 54. What happens if we put if we put 3 in there? Again, we get 81 minus 27, so that's 54 also. Well, since these are equal, what can we do? We can use Rolle's theorem, can't we? By Rolle's theorem, there has to be one between -3 and 3. So we know we should expect to get at least one answer out. So let's take the derivative down here. F prime at C is 4x cubed minus 6x. Set that equal to 0. We can factor out a 2x, and we get 2x squared minus 3 equals 0. Well, this gets us x equals 0. So we've got one. Are we finished? Well, what did the direction say? It said find all values on the interval. Do we know that there are more? If you go back to algebra, we've got an x cubed, so we expect 3 answers. So let's see what other answers we can get out of this. 2x squared equals 3. X squared equals 3 halves. So x equals plus and minus the square root of 3 halves. Is that less than 3? Well, 3 halves is less than 3. So if we take the square root of that, we're still going to be less than 3. So now we've got 3 points, 3 critical points in our region that we're looking at, in our interval from -3 to 3. So we found our 3 points, 0, plus and minus 3 halves. Well, how does this help us? Well, suddenly we can figure out what's going on with these 3 particular points. We can know a lot about what this graph's going to look like. So let's just take a moment and try to look and see. We know that at 3 it's at 54, and at -3 it's 54. Well, what else do we know? We know it has critical points. We know it has the derivative equals 0 at 0, and then at square root of 3 halves and negative square root of 3 halves. So we know this function has to go down, and if we plug in 0 at these places, we find out that the function is going to be 0 there. So we can suddenly figure out that we know this function has to do something like this, maybe. in there. Now how do we know it does that? Well, we know that it has to have a derivative of 0 at these three places here, at 0, at plus and minus 3/2 in here. So we've got those three. We know it's got a function value up here. Can we talk any about what's going on out here? For example, does it keep going up, or at some point does it turn over and go back down? Well, let's see if we can determine that. What's going to happen if it turns over and starts going back down? It's got to have a tangent line that has a horizontal tangent line, which means it has a slope of 0, which means it has a derivative of 0. But we've only got 3 points that have a derivative of 0. So we know that this could not happen right here. So we know then that already that the function has to keep going up out here on both ends. So with just a little bit of information, we've learned a lot about this function. Now I don't want you to get bogged down in what I did over here on the graph. The main thing is understand that we can do this part over here because of Rolle's theorem. Be able to do this part over here to find these critical points so that you can learn more as we move forward here. Well, let's look at this problem. It doesn't say Rolle's or mean value, but I think we'll find that one of them applies here. Given that we've got a function, find all values on the open interval such that this is true. Well, it doesn't say Rolle's or mean value, so let's just jump in and start doing some math. Can we figure out what f of 4 is? I think we can. F of 4, if we plug 4 in there, we get 5 minus 1, which is 4. If we plug in f of 1, we get 5 minus 4, which is 1. So let's plug those numbers in over here on this side. We get 4 minus 1 over 4 minus 1, which is 1. Does this look familiar to something? If you'll go back a few slides, you'll see that this looks an awful lot like mean value theorem. We've got function values are not the same. We've got a continuous and differentiable function. So there has to be something in here. So we expect to get a number between 1 and 4 that will make this true. So now what does this problem down here say? Look at this as simply a math problem. The derivative is equal to this. So let's find the derivative. What is f prime of x? Well, it's 0 for 5, negative. If we think of this as 4x to the negative 2, we can simply use our power rule and say that's 4x to the negative 1. My apologies. So it's negative 4x to the negative 2. We've got two negative signs. So the derivative is 4 over x squared. What does it say? The derivative has to equal 1. So if we write down 4c squared equals 1, if we cross multiply, we get c squared equals 4. We get c equals plus and minus 2. So which one are we looking for? Both of those answers? Remember, our interval is from 1 to 4. So we're only looking for c being 2. That's the only one that's on our interval here. So c equals 2 is our only solution to this problem. Negative 2 is not a solution because it's not in the interval. And that's all we're asked to find. This has real life implications here, and let's talk about it with a problem that any of us could be faced with here. We've got two state patrol officers sitting on Highway 316, and they're exactly 5 miles apart. So we've got one officer, officer number 1 is here, officer number 2 is here, and they are using their radar guns. So truck goes by here, officer looks at his watch and sees what time it is, and the guy's going 55 miles an hour. So he can't give him a ticket. Let's say that's at t equals 0. Well, he radios down to his partner. 4 minutes later, the partner sees the same exact truck. He clocks him doing 50 miles an hour. Well, his radar won't let him give him a ticket either. But can we use any math to say that this guy had to be speeding in there somewhere? Because we can make the assumption that he was driving all the time because he's on the road here. So is there any way it's continuous? We could say that these two what can we say about these two here? Well, over this distance here of 5 miles, he's covered 5 miles in 4 minutes, right? Well, that's just rate distance divided by time. That gives us a rate. So he went 1.2 miles per minute. Is that speeding? Well, that's kind of hard for us to figure out. So maybe we need to change this and make it 5 miles divided by how many hours did it take him? It took him 4/60ths of an hour, didn't it? 4/60ths of an hour, because there's 60 minutes in an hour. Well, that's 5 times 60 over 4. And if you do that, you find out 75 miles per hour. So was he speeding? Well, his average speed was 75 miles an hour. That means if we look at the difference in these two ends, it's 5 miles, but in only that length of time, only in 4/60ths of an hour, is 75. So what does that mean? By Rolle's theorem, he had to be going 75 miles an hour somewhere in here. In fact, he was probably going 75 miles an hour most of the time in here, and just slowed down at these two places that we found. So if the officers had all of the data, they could in fact charge the man with speeding, even though their radars didn't say that he was speeding at those particular times. This is very confusing, and this is a concept. I don't want you to get bogged down in the concept. I want you to realize that the concepts are here. Realize that we're going to continue working with the concepts, and as you look at the problems, try to read the problems, try to understand what they're asking you to do, and practice the skills that we've already learned. I think that you'll find you know more about this than what you may think at this time. Feel free to come back and look at this video at a later time, though.